continuing from last lecture, this was a simple example of a switch capacitor, integrator, and then by putting this equivalent of resistor, which is a capacitor C1, getting switch between phases phi 1 and phi 2, then we will get the equivalent of this circuit, and then accordingly we can write and derive the transfer function of this simple integrator in discrete time. And okay, so then when you want to see how it will be, okay, so in phase phi1, Vin will be stored on this capacitor, so it is converted into charge, and next phase this charge will be transferred to C2 symbol. Therefore, we can have two phases phi 1 and phi 2, and both belong to same cycle. Therefore, we consider this is one cycle, and again phi 1, phi 2 is the next cycle, and accordingly V out always will change only in phase phi 2, and the charge will be stored in phase phi 1. Therefore, if you simulate, you will see this step type of output, some sort of step with different amplitudes, and because it integrates input, therefore if you apply, for example, a constant input, you will see it will be like a staircase. Depending whether it is positive or negative, whether it emulates a positive or negative resistor, it will be a rising or falling staircase. So, for example, you can consider you are very close to edge of phi 1, therefore the signal you will get will be exactly on the capacitor will be V in N, which is sampled in that particular phase at the edge of phi 1, when phi 1 goes from 1 to 0. We consider 1 for the case when switch is closed, and if input is 0, clock is 0, then switch will be open. Therefore, you need just to write the equations, and the way equations are written is always we look at the charge redistribution between capacitors. Considering op-amp is almost ideal and the amount of input current is almost 0, therefore we don't have any current which flows through input capacitance of op-amp, means it's almost negligible. Therefore, the entire charge which is stored here will be transferred to capacitor C2, and this charge will be transferred completely. Therefore, we consider time cycle T is enough large so that the delay of this discharge, which is due to the finite value of resistance value of this switch, will be enough so that this capacitor will be almost discharged completely in this C2. So C1 will get discharged in C2. So C1 will lose the entire charge, therefore there is no problem with C1. But for C2, you need to note, every cycle we have some charge already stored on C2 from previous cycle. Therefore, charge which is added to this capacitor will change the charge from original value, which was C2, into V out n minus 1, into the new value, which will be C2 V out n. And accordingly, you can write this equation. So that's why we have this V out n minus 1 as initial state already there, and then now we will have a delta Q. So then it's very simple, and this delta Q is same as charge which was stored on C1. Therefore, you just replace it by C1 V in n minus 1, and then you will get a simple relation for this integrator. And therefore, finally, you will get a transfer function of integrator, which will be forward Euler. And of course, because forward Euler, as we discussed last time, may lead to instability, therefore it is better to use a scheme which emulates backward Euler. So now we will continue in this lecture with backward Euler implementation and other and bilinear definition and implementation and example circuits. Okay, so we want to design a bandpass filter. So this is omega, and this is magnitude of J omega. Okay, so it has a center frequency of omega 0 and corner frequencies omega 1 and omega 2. Okay, so this is what we want to design, and to avoid any confusion, at low frequency gain will be 1 upon 2. So you know, because in low pass filters also will be 1 upon 2, it's not normalized, it's the real value. So omega 1 will be 2 pi into 6k radian per second. Omega 2 is 2 pi into 8k radian per second. And this omega 1 and omega 2 are minus 3 dB frequencies from both sides. Okay, so we want to design a simple LC ladder filter for this, and then you need to convert low pass to band pass. The relation for conversion also is this. If you want to get band pass, and B will be omega 2 minus omega 1, and omega 0 is 1 upon root square omega 1 omega 2. Correct. Omega 1 omega 2. Thanks. Yeah. And you consider we have a simple low pass filter with this simple relation. Okay. Therefore, it's very simple. Just you convert this low pass to a band pass, which will have this characteristic using this relation. And Sn is normalized frequency, so it will be S upon omega. And just you realize the filter and get values. It is S because it is effectively normalized. Means that this is for R equal to RL equal to RS equal to 1 O and omega minus 3 dB also is 1. So it's normalized. For bandpass also you consider RL is equal to RS equal to 1. So it's just frequency. Realize the filter using LC. Come on, it's very simple. Derive everything and then at the end you replace numbers. That makes it faster. Okay, whatever you have written, you will learn it, no problem. But always see you write relation in the form of parametric relation. At the end you replace parameters by numbers. That's the rule of thumb. Okay, so then it's enough. Just the whole motivation is to always review things, small things. And usually what I ask in the class, usually I give quiz from those questions. So at the beginning also I gave you this hint. So like this noise. So because I asked you to find out this conversion, I gave you hints if you remember for low pass to band pass, and then I ask you, okay, you check it, and then, but when you don't come back, then means that, okay, you have done it, I assume, and then it is okay and well understood. Okay, but anyway, it was, it is simple, just I will replace the values, right? It was just replacement. It's very simple. So this relation is very useful when you want to design a band pass. Okay, so H low pass was 1 upon 1 plus S. Here, of course, will be 1 upon 2. Just we will replace, right? So when you replace, you do, as I said, don't convert anything to number. Keep it as it is, okay? So H band pass will be this replacement, right? 1 upon 2, 1 plus. You just replace it. Therefore, it will be omega 0 upon B SLP square plus omega 0 square upon SL. Right? SLP in fact is the loop. When you have this is SLP. Okay? And then in band pass, what we do is we say S band pass is equal to, you replace now SLP to S band pass, which is equal to omega 0 upon B SLP normalized plus 1 upon SLP normalized. This was the relation, right? So then SLP normalized is SLP upon omega 0. You will be getting this, and simplified one will be 1 upon 2 S2 plus omega 0 upon Q into S plus omega 0 square, and this will be omega 0 upon Q. Omega 0 upon just a minute here. It will be, let's calculate it again. Okay, so it will be 1 upon 2 B SLP and 1 plus omega 0 into SLP square plus omega 0 2, correct? SLP square, this is normalized, so it will be upon omega 0 2 plus 1, this will be upon omega 0, so this omega 0, okay, yeah, this will be omega 0 upon 2, and then here you will have 1 upon omega 0, yeah, correct. So these two get cancelled, it will be 1 upon 2, 1 plus SLP square plus omega 0 2 plus B, not 1, plus B as low pass, and then this will be B as low pass, correct? Therefore, HS in general will be 1 upon 2 B S upon S square plus BS plus omega 0 square. And at S2 equal to omega 0, it will be minus omega 0 to omega 0 to B, and B will get cancelled. It will be 1 upon 2. Therefore, we will get this. 1 upon 2. Okay, so then when you get HS, now you can realize LC. Another way would be like, instead of reaching to this and then realize it, you realize H low pass and then use that transformation to convert a single L to LC. The second approach. And this is because this is second order, it's actually very easy because see, simply you can make it like this. I don't write it. All are 1 L C. Because you have just a second order filter. So this is the out. And resonance frequency is 1 upon root square L C. In this case, it's very easy. Omega 0. That you have already, and omega 0 was root square of this 6K and 8K. So transfer function for this, V out upon V in, will be 1 plus SL plus 1 upon SC plus 1. Right? So it will be SC upon S square LC plus 2CS, this will be 2CS plus 1. So if you divide by LC, this will be S upon L, S square plus 2 upon L, 2 upon LS plus 1 upon LC. Which again, at S square minus 1 upon LC will give you 1 upon 2. So now you compare it with this. 1 upon 2 BS upon S square plus BS plus omega 0 square. Therefore, you will get correspondingly value of 1 upon L will be B and 1 upon LC will be omega 0 square. Then you will get value of LC. Second way will be like you have a low pass already. That transfer function, I think it can be like this. One sum L low pass. So or this is another. And then use frequency transformation. So then this L will be converted to LC. Any question? Yes, shunt also is possible. But here, because we are talking about voltage, we will use series. Shunt will be used for current. Yes. And essentially using, you see, this second order circuits is very easy. That's why in many applications people use the second orders. Okay, so now see, effectively this biquads, this second order, you learn this relation. This is a very useful relation for band pass, low pass and high pass. Because just S changes. If you remember, for low pass, this was for second order low pass, this was just a constant. For band pass, it will be S, and for high pass, it will be S square. Now, there are general purpose second order modules which are available. Standard. You don't need to memorize them in design references. That give you all of them by using 3 to 4 op-amps. Therefore, you would be able, they are essentially multifunctional modules, biquad modules. Then they are used as a standard way of designing multi-order filters. So then, after this, when you are able to get this, then the problem is solved, because then converting it to any sort of filter, including GMC, including active RC, is very straightforward. Okay, so coming back to this, so how to make the backward Euler approximation? This is backward Euler approximation. Okay, so this circuit is very interesting. Now, see, how to avoid delay. What was the point with forward Euler? Forward Euler creates a delay. Now we want to remove this delay. What does it mean? In forward Euler, we would charge the capacitor and then discharge it, right? Now what we do? We charge and discharge it at the output capacitor simultaneously. And then we reset it to 0 in a separate phase. This circuit does that. So in phase phi 1, as you notice, C1 gets charged, and at the same time C2 also will get charged. Because the current which flows across terminals in C1, it should flow through C2. There is no other way, right? Therefore, we are charging C1 and C2 simultaneously. Then in phase phi 2 only, we discharge C1. Therefore, now this will be backward Euler because there is no delay between output and input. And if you write relations, you will get backward Euler relation. Do you remember I told you, you check it for integrator? This is like one way of checking. How do we can get that integrator approximation using this interesting switch cap circuits? So, just I equal it with -1 upon SRC2. R is emulated by C1, right? And 2 phases phi 1 and phi 2. This part is as before, right? Therefore, I have RC. So, just I make it equal to -1 upon SRC2. Therefore, I will get relation between S and Z. And this tells that Z is equal to 1 upon 1 minus ST. So, this is backward Euler. Do you remember in forward Euler it was 1 plus ST? You know what is that? If ST is small, 1 upon 1 minus ST will be 1 upon 1 plus ST, or vice versa. 1 plus ST can be written as 1 upon 1 minus ST when ST is small. So all these approximation are based on this assumption that ST is small. Means magnitude of ST is small. Magnitude of ST is small means that sampling frequency is quite enough compared to the maximum frequency included in the bandwidth of the signal. So that is a very interesting implementation. And there is one more implementation and approximation which is bilinear. Actually bilinear is very, I would say that the best transformation and approximation we'll see. And for this mini project also I ask you to use bilinear transformation to use this conversion. So what is bilinear? Bilinear in the integration, as we mentioned already, was just if you integrate from n minus 1t into nt xt dt, you approximate area below this signal waveform. This is xt and this is t. So suppose you want to integrate from this n minus 1 t and this is nt. If you want to integrate, we approximate this area by area of this trapezoid. Therefore, it will be x n minus 1 t plus x nt divided by 2, average of this. Therefore, it will be x nt plus x n minus 1 into t upon 2 multiplied by the height, which will be t. And this is, for example, if I consider this y t from n minus 1 t to n t. I write it in discrete domain, therefore just I replace yn, not nt. Therefore yn minus 1 n minus 1 is equal to 1 upon t upon 2 xn plus xn minus 1. Now we get z transform. Therefore yn into z, so 1 minus z inverse will be t upon 2 1 plus z inverse into, sorry, this should be yz. And this is x. Therefore, transfer function of integrator for bilinear approximation will be this. And again, similar to what we had, we want to make this equal to ys upon xs, which was 1 upon s. Therefore, this will give us the approximation. S is equal to 2 upon t, 1 minus z inverse, 1 plus z inverse. So this is a very useful transformation. Equivalently, you can get z. Z will be equal to 1 plus t upon 2 into s, 1 minus t upon 2 into s. Okay, so we had 1 plus ts, 1 upon 1 minus ts, and this is 1 plus t upon 2s upon 1 minus t upon 2s. So this approximation is a more accurate approximation. How it will operate? So we have this axis j omega, and this is analog frequency. Okay, so this area is of interest plus this area, which usually we have zeros, for example, because of loss. How it will be converted in digital domain? Okay, interesting point. If you look, if z is equal to e to the power j omega, what will be magnitude of z? Z will be 1, right? Now suppose if I consider mapping from j omega, that is a very important mapping. If you remember, that was creating problem in other approximations. Where it will be? Where j omega will be converted in this outside? See, you just replace sj omega. Where? On the unit circle. Because if you replace s by j omega, magnitude of this z will be 1. Therefore, this is a very correct approximation for this axis. Therefore, we will get everything on the unit circle for frequencies on the j omega. So that is interesting, because then we don't lose anything, right? If we have loss, still we will get loss at those frequencies, which was not already available for us. So this will come here. Therefore, j omega will be mapped on periphery of unit circle, and left side of j omega, of course, will be mapped into the inside area. Okay, so this is for bilinear transformation. So what is this transformation? Of course, it's not a completely linear, but just if you replace, so z is equal to e to the power j omega dt, and s is equal to j omega. So if you just consider these two in this relation was j omega is equal to 2 upon t into 1 minus z inverse, which will be z to the power minus j omega dt. Sorry, it doesn't have t. J omega d, capital D, not a small d. 1 plus e to the power minus j omega d, capital D. If you just, take common factor of j omega dt upon 2, then this will be sine, this will be cosine. After all, you will get this relation. Omega is equal to 2 upon t, tangent of omega dt upon 2. So if we plot it versus omega dt into t. So when omega dt is pi, tangent pi upon 2 will be infinite. Therefore, like this is pi minus pi and then 2 pi. So in that case it will be infinite. And when omega d is 0, this is 0. Therefore it will be. Yes. 2 upon t. This is 2. This is pi, this is 2 pi. And 3 pi. Again at 2 pi. As pi this will be 2 pi. At pi it will be pi upon 2. At 2 pi it will be pi. Therefore it is 0. Therefore it is unitary. And then same here. Okay, so now how to implement it by a circuit? Because till now we had only backward and forward, but how we can implement this averaging? So we should make a circuit which will get average of these two charges, right? Xn and xn minus 1. So this will be the circuit. These are very interesting circuits. See, notice whatever ground I show is AC ground. When you want to simulate and use real op-amp, then it will be a reference voltage. Okay, so this is the output part. Always this output part is constant because that is the integration part. What we want now to make this charge which is coming here to be average of input signal. Therefore, this is the arrangement. We put a capacitor with switch. Okay, so this was as before, phi 1, and this was C1. Now we want to make average. We make it C1 upon 2. Okay, and again we discharge it in phi 2. So what to do to make it average? What we want to do, in first phi 1, when this switch is closed, we don't want the entire charge to go here. We want half of it to go. That's why we make it C1 upon 2. Another thing is we want to have a memory of xn minus 1. And then send the charge related to x minus 1 also here, right? So to do this, we need to have another capacitor. So we add one more capacitor. So this was the first part, right? So we modified it in this way. So phi 1 and C1 upon 2 will be there. So this is the component I have already, C1 upon 2 and phi 1. And this was 0. So I need to add a memory. Therefore, I need to take sample in preview cycle, right? So I add phi 2, therefore, it's the preview cycle. Store it on a capacitor. This is also C1 upon 2. And transfer it in phase phi 1. So the whole idea is the charge which is coming here, if you call it delta Q, now this delta Q should be an average of V in N and V in N minus 1. Now if you just, so do you do this for, that will be useful also, because when you start writing this equation, you will get this skill to derive the equations. So you derive delta Q and then so you will get this relation of bilinear transformation. This one? Yeah. This one.
Why can't we have a similar one and to average the other one? If I will do
no, but the point is that then we need 3 phases, because what we want to do, we want that the phase we sample We want at the same phase to transfer it to output to avoid delay. But if you want to add this arrangement, then means that output need to be, revised or updated in the third phase. We want to make these two to be simultaneously. And in fact, even this, if you look at this part, these three are done simultaneously. So therefore, I don't change this path. What I change is this path. This was for the discharge, right? I just, instead of discharge, I make it this. But still, I should have this phase, right? Because this need to get discharged. Therefore, I will add this. Okay, let's see. No, sorry, yes, because this should discharge it. Sorry, yes, correct. Yeah. Phi 1 will be open, then phi 2 will be closed. Okay, so then you derive transfer function in Z domain. And of course, also derive difference equation. See, in continuous time, we have differential equation and we have Laplace transform. In discrete time, we have difference equation and Z transform. So the difference equation will be same as like this. This is called the difference equation. Okay, so now you know the building blocks, right? Therefore, now it's very easy to make a switch gap. So, because when you have this building blocks, if you remember, from SFG, we derived integrator. And this is discrete integrator. Therefore, from here onwards, everything will be systematic. Okay, now let us see. Suppose you have a continuous time filter. How do you convert it to a discrete filter? So, coming back to that biquad we had. Okay, this is a second order biquad. So you have design, you have continuous time equivalent of the circuit or realization of the circuit. V in R C1 C2 R. Okay, V out. This was a low pass filter. Okay, and Q was ratio of capacitors. Now suppose you want to change this to a switch gap, right? You have designed everything and value of R and C1 and C2 are correct. So what you need to do, you need just replace, right? Because you know frequency, sampling frequency always is known already. Therefore you need to T. You don't touch capacitors, they are as it is. You just replace resistors, right? So simple. So what we do, for example, you want to implement R, right? So we need to implement R. Now it depends which approximation you want to use. For example, if you want to use bilinear, means you need to replace it by this, right? If you want to use backward, then means that you need to replace resistor by this. Therefore, it's straightforward. Q was root 1 upon 3 root square C1 upon C2. I mean, proportional to the ratio, root square of ratio. I think it's C1 upon C2. What is important is Q doesn't change with the process corners. Okay, so then we'll, before going with this, okay, so then this is a straightforward, just you will replace. For example, for R, if I want to go with backward, then backward was this. And then here you will have C1. and again next R. Right? So similar. Because all R are equal, then we will have same. And so on for this. And then here will be R. Done. Okay, so now you have converted biquad, second order low pass biquad to an equivalent switch. Yes, correct. Sorry. No, yeah, correct. Right. Sometimes it happens, we can even simplify more. The reason is because some of these switches come in such a way, they will operate simultaneously. Therefore, you can remove them and then just connect them. See whether something is here or not. Can you simplify? Because this is helpful, you can reduce number of switches. Yes? These two by one. Then this means that you need to connect these 2 points. Because if, see in phi 1 they are connected. But in phi 2, if these two are connected, no. But then you have 3 nodes. Removing from here. But then the point is, if this node was connected here, yes, but this node is connected here. Sometimes it's not possible, sometimes it's possible. Input. Your question is then, but if you want to shift it, then you need to connect these 2 points. No, but if you connect, you know what happens is then you have these 2 connected to the capacitor. If it is not even connected to capacitor, you make it 1 and then connect these 2. Now you see, look at this situation in phase phi 2. You have these 2 nodes connected. Therefore, it is likely to have some charge sharing. The reason is because when these 2 are open, you are sure that the entire current will get dissipated here. But when you connect these 2, and this is a path, right? So this charge may come. Of course, this is short circuit, but practically you have a resistor here. Practically, this is a resistor, therefore, and these 2 are connected. Let's see. It will be like this. And then this goes to op-amp. You have C2 and this is output. This is phase phi 2 and this is open. Yeah, correct. Because these 2 will have charge sharing. CR, and C2. Look at this loop. So here it's not possible. So this is not correct. It's not possible. So reduction is not possible here, but there are many cases it's possible. I actually put an example for you, but because it is for this strain sensitive, I need first to talk about it, then give you an example. Okay, so now coming back to this backward. Okay, by the way, what is value of CR? This need to be done, right? Because C2 is same as before, C1 is same as analog, only CR. Therefore, R was T upon C. Therefore, here it will be C. Okay, now it will be very interesting. If, for example, filters you have designed till now, you just derive the switch cap, even you can start the first order simple filter. Derive it and then simulate it. Usually it's better to keep it in the assignment also. I have given at least around 7-8 times more. But practically even twice of this is used, but it's better to keep it more than. Because signal always has a tail. It's not perfect. It depends on the application. See, for example, in biomedical, really low sampling rates are used, and it doesn't create any problem. Like sampling rates as low as, for example, just 2.5 times of signal bandwidth are used. So, this is backward Euler approximation. One of the problems with these architectures is circuit is very sensitive to parasitics, because these switches are not real, are not ideal. Therefore, they will have parasitic capacitance. So, showing parasitic capacitances in this way. Always you will have additional capacitances here. So I am adding here, but it's not a part of this derivation, just I'm showing parasitics. So these are parasitic. So what happens is, because for example in phase phi 1, we want input is here, okay. Now of course look at this circuit, essentially how it will behave. So we have some parasitic capacitance here, and of course this will be connected to V in, this will get charged, and we have this phi 2 when C1 is getting discharged. So if phi 1 is, if switch S1 is not ideal, then voltage here won't be exactly V in. But then if we give it enough time, then this will get charged. And then when it is getting discharged, this charge will remain here. Actually here I don't see any problem, because this parasitic capacitance is connected directly to V in at the left side. This cannot create any specific problem. And charge transfer will be done in this state. And this capacitor C1 will get discharged completely in phi 2. Therefore, here I don't see any problem. Because parasitic capacitance will be a problem if it contributes to the amount of charge which is transferred to the output capacitance. Yeah, but Vn changing, see, because anyway, if we give it enough time, Vn is here. Therefore, the amount of charge which is stored on C1 still will be C1 Vn. There is no other charge. Actually, that's interesting. Why this should be sensitive to parasitic? This is forward Euler is sensitive, that is well understood, but this I'm not sure, because this is a resistor, right? So this resistor will conduct some current, right? And these two capacitor will charge to the new values. If you give it enough time, then after some time this current will be almost zero. Therefore, you won't have any drop here, and this node will reach to Vin. And the charge, in fact, that additional charge is coming from this Vin. Therefore, it doesn't have any impact on this. Yeah, there is one point here. Because when you open the switch, there are two things. One is clock with true, and one is discharge of charge which was stored on the channel of phi 1. Right? So that will happen, and this will go through this and this as well. Therefore, this will create charge. Yeah. See, if you have a transistor, this is the switch. For example, an NMOS switch. This is clock, and one side is connected to, say, Vin, and this side is connected to next part of the circuit. So there is a parasitic capacitance here, and there is a capacitance from this node to ground. So there are two effects. First of all, when clock goes from low to high or high to low, specifically high to low, because when it goes from low to high, anyway, finally this charge will be equal to CVE. So when clock goes from high to low, means this switch is getting off. At that time, there is a capacitive division here. Therefore, some charge will come here. And this charge is negative. Because this is falling edge. This will fall. Okay. So this is one delta Q which will happen when this switch is opened before this switch gets closed. The second thing will be this was on, right? So charges which are stored here need to get discharged. Some part of these charges may come into this capacitor. Therefore, we will have 2 delta Q. This delta Q1 is due to clock with true, and clock with true is this capacitive division. This was C, this is C parasitic between gate and source, and this was clock. So falling edge, if it is very sharp, will create a delta Q on the C. And delta Q2 is because when switch is getting off, some part of the channel charge, you can look at it as a distributed RC. Some part of this channel charge will come to this capacitor C, which is connected to the source. So this delta Q2, which is charge which was stored in the channel, when transistor goes from on to off. Therefore, these two will change charge which was here and as well as here. Therefore, we will have a change in output voltage. So, still phi 2 is not operating. So, these two are non-overlapping phases. Therefore, when this S1 opens, this phenomena happens. Clock with true and charge distribution or charge fit through, in fact, charge fit through from the channel. And this charge fit through will change this voltage, doesn't matter, and some part of it will come here. And then will go into C2 and then be out. And the amount of charge specifically which comes from channel depends on value of Vin. It's not a constant value. Because if it was a constant value, we could just use offset compensation. But it's not a constant value. Therefore, it changes with Vin. Therefore, it creates nonlinearity. So, therefore, it's always better not to use capacitances in this fashion. We have to create a path to ground which allows this additional charge will go to ground, or use some tricks for switches. For example, for clock feed through, you may have seen, if you have this switch and you have a clock here and you have a capacitor here, or it might be connected somewhere else, not necessarily to ground, wherever is connected. Now if you put additional switch in the form of a dummy switch and connect source and drain, and then now you give clock bar. So suppose aspect ratio of this switch is W upon L, aspect ratio of this switch will be W upon 2L, or in fact W is half. Because you have connected source and drain, therefore the effective capacitance you see will be from gate to drain as well as source to the gate. Therefore it will get multiplied by 2, so we use half. Therefore effectively these two capacitances are same. If you call it C parasitic, PR, and this also will be CPR. Now when clock goes from high to low, clock bar will go from low to high. Therefore the charge which was coming here now will be absorbed by this and nothing goes here. So putting a dummy switch, for example, is one of the ways to avoid this clock feed through. And another way is to make this capacitor quite large compared to this parasitics. Therefore it is always preferred to connect everything to ground. Okay, so this is clear how this parasitic. Yeah, see, for example, look at in this way. You have two capacitors, they are equal. And here you have delta V, here you have minus delta V. Okay, and this will be 0. No, this is transition. This is happening at the transition, clock transition. Not when clock is stable. At that time everything, there is no change. Capacitors are open. This happens during transition. So you have a delta V, for example, negative here. You have a minus delta V positive here. Look at it as an AC signal. So now common mode of these two AC will be 0 because this is a symmetric circuit. Therefore, when this is 0, what does it mean? It means that whatever is connected here won't see any change. Therefore, no current will be. So therefore, always it is preferred, whatever parasitic we have, and they are important, should be always discharged to ground. No, again in opposite transition. Again the same. Now it will be clock, bar and clock. In opposite phase, same thing will happen. No, it doesn't need to discharge because it doesn't need to discharge through this actual because always these two exist, right? It's just the polarity which changes. Therefore, always charge and discharge will be through these two capacitors if they are completely matched. Yeah, because this, we don't mind whether sign is positive or negative. This is an off transistor because source and drain are connected. Therefore, it behaves only like a capacitor connected between this node and plug. To draw an example of this connections. Of course, this we had in VLSI lab. Yeah, I remember I showed you. One was, for example, for phi 1. For phi 1, what was the situation for forward Euler? This was the connection. Okay, and this goes to integrator, simple case. No, here, just we want to see, anyway, here also there will be parasitics. This also will have some parasitics. So we want always to make sure that all parasitics will be grounded. That is the best thing. So we make just a modification will be to keep this capacitor as a float capacitor. So we have here some parasitics to switch in parallel to this. So we always use it as a float capacitance, and here there will be another phase which forces any capacitor which exists between this node and ground will be discharged to ground. Similarly here. And then C. So in one phase we want to charge it. Therefore one phase will be, for example, this. Phi 1, Phi 1. One phase we want to charge capacitor C and discharge C1. Therefore next phase will be Phi 2. You mean adding number of switches? Yes, of course. Right. Oh, yeah. I mean, that is the price. Yes? Yeah. Means that anyway this will limit your frequency. But the point is that usually in switch capacitors frequency is not very high. Because this type of capacitors, the filters are not used for very high frequency signals. Anyway, usually this is not a constraint. As long as we are dealing, for example, look at audio signal, you get biomedical signals. All of them are low frequency. And then if you have a switching frequency of megahertz, it still is okay. Yeah. Yeah, clock and clock bar should be almost synchronized. See, these are all, in fact, nobody says that it is an ideal solution. Nobody can say that there won't be any leak here. For example, this will be perfect and clock bar will have exactly the same edge. But it is possible, usually like, good clock generator is possible to adjust the delay between, see, for example, how do you design a clock and clock bar which are synchronized? You use one inverter, two inverters, and here you use three inverters, okay? But they are not of same size. And then you adjust so that these two paths will have same delay. So they are of different sizes. So that's why 1, 2, and then 3, 4, 5. This is one of the bases. So now similarly, okay, now what happens is always in one phase, this node which has parasitic capacitances is connected to ground. Whatever charge we have will be always grounded. It won't transfer through C. So therefore, suppose for example, when switch phi 1 is open, right? That was the problem, right? Some charge will come here and some charge will come here. But then in the next phase, when we want to transfer it to C, we close this switch. Therefore, same charge will get, the charge which was stored here will get discharged completely. And when it gets discharged, therefore, the same charge which has gone here, that also will come back to the ground path. Therefore, what goes here will be the net amount of voltage which was stored on C1 at the beginning. So, if you remember, we had this in VLSI lab also. So I think the same circuit I asked you to simulate. And similarly for forward Euler, for backward Euler. Again, you have this capacitor C1. So we wanted to discharge it at phi 2. So we connect it to ground and we discharge it. And then phi 1, it will be directly connected. Or for example, one of other ways is to use complementary switches, because when you use complementary switches and clocks are exactly synchronized, then you would be able again to do same thing. because but it's usually difficult to do because it's very difficult to match these two. If you can match these two capacitances properly, which is usually difficult, then this also will solve the problem of clock fit. That's why the first method is preferred, putting the dummy switch. Okay, so is it clear? Therefore, whatever additional charge we get here, it will get discharged to the ground. Therefore, no charge, which is a function of V in, will be transferred to output. This essentially means always we keep this left plate at 0 level. Therefore, net charge won't change. This is for forward Euler. For backward Euler will be this. Forward Euler is and phi 2 we are transferring to alpha. No, this was the earlier case. In phi 1 we charge it, in phi 2 we transfer it to alpha. Okay, you mean the polarity? Yes, yes. Polarity has changed now. Yes, yes. We will get negative. Correct. Yes. Yeah, that is the important point. Here is positive. Now what happens? We are transferring from negative side. Yes. Yeah, exactly. Exactly. Because see, of course, there are two things. If clock fit true, which happens when phi 1 goes from low to high, that always can be compensated, because if we give enough time, this node will reach to V. Therefore, none of them will sense it. But when phi 1 goes from high to low, then there will be change in the charge due to clock fit true. And no, but then we don't need, because after all this also will get discharged. No, see, because if you have clock fit true, see, there are two things. One is clock fit true, one is charge sharing. If I can solve both of them by this technique, if I have clock fit true, then means that this potential will rise. What does it mean? Means that I have some charge which has come here, some charge which has come here, right? Now, when phi 2 is closed, both of them will come back to 0. Therefore, I should not be worried about it. I think that will solve the problem. Let me check this. I believe this will solve both problems. I will double check it. But I believe at this moment, both of them anyway are coming here, and both of them will get discharged to ground from here and from here. So net current will be 0 at this point, net charge. So the question is whether it will be a unique solution to both. Okay, so now what I suggest for your project, it's just a simple second order elliptic filter, because I have given a specification in such a way it will be second order elliptic. Then it will be easy to just get it done and then get the architecture of the filter. Then you use proper switches, sampling frequency also is not very high, therefore you would be able to implement it easily. You can use only full NMOS or you can use complementary. I have not given any constraint on the input signal amplitude. Therefore, you should be able, you can use any amplitude that you want. And one more thing is, I don't think either Mentor or Cadence would be able to use, to simulate, AC response. Therefore, you need to get it at few frequencies. So means that you do transient analysis. In last semester, we did it using sequence. See, because when you want to use AC simulation, you need to sweep frequency and get the transfer function. But switch capacitors are circuits that you cannot, you can, of course, there are papers which talk about small signal models for switch capacitors. But I'm not sure. You can just check if Cadence or Mentor can do this. Otherwise, the way we do is we simulate at single frequencies. We do a transient analysis at a given frequency. We get the amplitude. We have amplitude at the input, amplitude at the output. That will give us the ratio. So for this, that's why I have specified only the few frequencies. But if they are able to do it, then you don't need to. You can just use frequency sweep to get the AC response. That you need to check. Last semester, I remember one of the students told me like there are programs similar to SQL which are able to do it. But now because we are using this and technology is UMC 0.18, so it's better you use mental graphics. Mental graphics and Cadence for this assignment. By the way, the parameters, just to have the parameters. It is 0.3 volt, U0314 centimeter square per volt second. This is just if you want to see how to design switch. In general, you may get everything from simulation. This is mu0 Cox. So this is for NMOS. And for PMOS, VT0 is minus 0.46 volt. U0 is 114.5. And U0 Cox is almost 94 microampere per volt square. Anyway, I am available. If you have any question and discussion about switch capacitors, every day 8:30 to 9:30 I'm available. And I'm following Schumann book, chapter 8. But he is using some other different notations. I may use different notations. But concept and everything is same as that book. And of course, Baker book, Mixed Signal Design, that also has a chapter on filters in general. So it has everything in brief, but you may have a look.